All right. Well, thank you, Cherie, and thank you everybody for joining us around the world. This is really exciting, and I'm excited to see what this grows into and how we can continue to do these types of virtual seminars. So this study is an interesting one for me because in addition to um, basically being a complete compilation study, the results that came out of the study were unexpected, and I was surprised at the results. Um, and and it's trying to address an age-old question of whether the continental crust grew rapidly over specific time intervals, so an episodic crustal growth, or whether crustal growth has been more or less steady state over the past few billion years. So here's a compilation of crustal growth models that June put together a couple of years ago, and as you can see, they're all over the place. There's lots of different crustal growth patterns, different magnitudes, and one of the things that was really useful with this 2018 paper that June did was he broke these up into different types of models. And so starting out, we've got surface ages. So these are the estimate of ages of rocks that are currently exposed at the surface. So we know that this line by Goodwin forms the absolute minimum of crustal growth because that is the proportion of rocks of different ages that are currently present on the Earth's surface. And then we have crustal-based models, and these crustal growth models are generally constrained by isotopes of zircon, hafnium, and or oxygen isotopes. And these models kind of fall into one of two categories. It's either the steady state models like Dweem, Belousova, and Coronaga, or episodic models like those of Patchett and Arndt and Nelson and DePaulo and Reno, etc. And so this comes down to kind of the heart of the question that we're trying to address. Was continental growth, was crustal growth steady state through time, or did we see peaks and troughs of crustal growth through time? So we've got our episodic crustal growth models here, our steady state crustal growth models here. And then we've got another family of growth models that Coronaga refers to as mantle-based models. And these are generally constrained by neodymium isotopes of either mafic rocks or mafic and felsic rocks. And generally, these mantle-based models form an upper envelope of other crustal growth models, and so they generally show more crustal growth earlier than the crust-based models, and so they range from Rosas and Coronaga, which argues for 100% of crustal growth within the first few 100 million years, which mirrors quite nicely the, I guess, hypothetical growth curve of Armstrong back in the day. And we can, I guess, view these different types, these different families of crustal growth models as representing net crustal growth models, the mantle-based models, or formation age models, which are based on the crustal-based models. And so what we're seeing from the mantle-based models is our net crustal growth. We then recycle that crust back into the mantle to get our formation age or our crustal-based models. And then from the formation age, the crustal-based models, to the surface ages, we have our crustal reworking. And so this balance between crust that is formed and then recycled back into the mantle, and then crust that is formed and then subsequently reworked by subsequent tectonic activity. And so again, the question is, was this formation curve, this crustal formation curve, steady state or episodic? Now, a really interesting study by Steve Parman, published in Geochemical Perspectives Letters in 2015, tried to address this by looking at a large database of zircon crystallization ages, and he took detrital zircons through time to see how the age peaks changed through time. And so if you look at all of the zircons, and the N here is just over 114,000 analyses, we've got some peaks at about 2.5 and 1.8 and about 1.1, and then we have troughs. So this is not a surprise to any of us. And if we then break this up into the individual continents, North and Central America, we've got similar peaks and troughs in North America and Australia. But what really becomes interesting is when Steve evaluates detrital zircons that were deposited during specific time intervals. So here can everybody see my mouse? Is that showing up? Okay, good. So we've got in North and Central America, the sedimentary rocks that were deposited between 3.5 billion and 4 billion. And these are the detrital zircon from sediments of that age specifically. And then as we kind of march ourselves through time, we can see how those peaks evolve on different continents at different times. And so the thing that Steve tries to point out here, I've put here in blue, and he says reference lines are shown for peaks, solid lines, and troughs or dashed lines. These peaks and troughs persist in sediments of all ages and on all continents, indicating destruction of pre-existing crusts did not produce the age peaks or troughs. So what Steve is seeing is that this peak here at 2.7 billion in North America that was deposited in sediments between 2.5 billion and 2 billion, that peak stays the same throughout the rest of Earth history. And this trough at 2.2 billion persists through Earth history. And the same is true with the other peaks and troughs in the other zircon. And so according to these data, and I do have to agree with Steve that according to these data, it seems to imply that these peaks and troughs were constant through geologic time. And if that is true, then the destruction of pre-existing crust could not be used to explain the peaks or troughs, because if destruction of pre-existing crust were the main driver of these peaks and troughs, we would expect those peaks and troughs to change through time, to evolve through time. And Steve then tries different bin sizes. So we've got 500 million years here, we've got 1,000 million years, and then we've got 1.5 million years. And it doesn't matter with these three bin sizes, the peaks and troughs stay in the same location. So this looked pretty good, and doesn't matter which continent you look at, that it all holds pretty well true. But there were a few things that kind of popped out to me, and so in particular, looking at this age peak here in Asia and this age peak here in Australia, that seemed to be out of phase. That even though the overarching pattern show that the peaks and troughs stay constant through time, there were some out of phase age peaks, and then looking at a few others in South America and India. And so this got me thinking about actually his title, this time-lapse zirconography. And so can we find an explanation for why some of these peaks are out of phase? And if I can be a little bit critical of the choice of bin size, if we think about the various geologic cycles that we see on the planet, and this is from a paper that Ross and others published, where we have plutonic cycles of about 6 million years, arcmagmatic cycles of 20 million years, upper mantle transit times, whole mantle transit times, the Wilson cycle of around 300 million years, and the supercontinent cycle at 600, and then our speculative super ocean cycle at 1.2 billion years. So Steve has chosen a bin size of 500 million years to try and evaluate whether these age peaks are consistent through time. But at a 500 million year bin size, we might be missing all of the geologic activity, all of the in this case, zircon growth that is being driven by these other shorter wavelengths geologic cycles than just centered more or less within kind of the Wilson supercontinent cycle regime. And so, as some of you may know, I like photography and specifically time-lapse photography. And so where Steve refers to this as zircon time-lapse or time-lapse zirconography, I thought, well, how does this compare with just normal time-lapse photography? So I've got two time lapses on the screen here. The first is a time lapse that I took in Northern Australia, where I took one photograph every 30 seconds for 4 hours. And so you can see we've got a boab tree in the foreground with the Milky Way sliding across the background. And then we've got another photograph or time lapse that is not mine, but is an analemma. So it is one photograph per week for a whole year, and it's taken at the same time every day, or at the same time every Sunday on once a week for an entire year. And so what we're seeing here is the path of the sun through the sky, and where we have the winter and summer solstice at the apexes, and then the equinox here where it crosses over. So both of these are time-lapse videos, but they show very, very different things. And so if all we saw was the analemma, we would say, oh, well, there was an entire year with no night. Well, that's not the case, but rather our bin size has dictated that we only see the sun at a particular time on a particular day once a week through the year. And so if we apply this same question to time-lapse zirconography, if we just look at bin sizes of 500 million years, what is missing between the frames? And so what I tried to do is I then took the database of Steve Putz and others that was published just recently that has over 600,000 zircon uranium lead analyses, and basically just tried to reproduce what Parman had done using the voice database. So this was the Peter Voice et al. Database that Steve Parman used in his 2015 study, and then I'm using here the Steve Putz and others database from 2019. And I should also say that, just as a bit of a plug for Steve Putz, that he's currently undertaking a much larger compilation that will include not only more data, but more information about the data, where it was collected, the type of mass spectrometers, and so that's currently underway with a large number of collaborators. If we compare then the ancient sedimentary rocks and the modern sediments, so the detrital zircon ages from those, they match pretty well. We've got about 500,000 detrital zircons from ancient sediments, and then we've got about 100,000 zircons specifically from modern sediments. Now, modern sediments here I classified as basically anything under 1 million years old. And so, the detrital zircon from sediments that are under 1 million years old match broadly those of detrital rocks that are older than 1 million years old.
What bin size are you using? What bin size?
Sorry, say that again, Kent.
What bin size are you using there?
So this is a kernel density estimate here, and so this kernel density estimate uses a bandwidth of 20 million years. So it's similar to the bin size, and so we've got here a 20 million year bandwidth. So then doing time-lapse zirconography on this larger data set at 100 million year bin sizes. So we've got the global data sets at rocks that were deposited between 3.5 to 3.4 billion years. It's not a lot of them, right? There's 229 zircon. Has an age peak centered at about 3.7. And then as we stepped to the next geon, the next 100 million years, 3.4 to 3.3 here in purple, And so you can see the dominant age peak at each of these time intervals marches forward in time. This is not surprising that you've got magma that's produced at this time, and so you have a large peak, then you've got magma that's produced at this time. I think what is curious to me about this is that in the rocks that are between 3.4 and 3.3 billion years, we see a strong age peak at 3.5 billion, but we don't see the previous age peak at 3.7 billion. And there are a number of these spectra that are more or less unimodal. Now, we do get into more multimodal components in the younger sediments. So then if we split this up into individual continents, and we can see that in Africa, we have a similar pattern through time. We've got multimodal at about 3.2, but what's curious is this peak at about 3.7 does not exist in these older rocks. And then we've got Australia, this large 4.1 GA peak is the Jack Hills, not surprisingly. But again, in general, the pattern is the youngest age peak marches forward with time. So this is just looking at Archean sedimentary rocks, seem to suggest that we did not have episodic crustal growth, but that we had episodic, or that we had continuous zircon growth over this time period. And so in between these ages, we had zircon growth at this time, and then that marches forward. So there are very few there's very few intervals of time where there is not zircon growth during the Archean. So then let's step forward in time a little bit to the age peaks associated with the supercontinents of Nuna and Rodinia. So I've got here for reference the modern sediment age peaks. And so we've got our age peak generally associated with the assembly of Nuna, and then the age peak generally associated with the assembly of Rodinia. So then comparing those to the various continents. So we've got Africa. So this is all of the detrital zircons from Africa, regardless of age, compared to the modern zircon, the modern sediment ages, zircon ages. And we can see it matches pretty well. Antarctica matches the Rodinia age peak very well, but has a much more diminished Nuna age peak. Asia has the strong Nuna age peak, but doesn't really see a strong Rodinia age peak, but instead sees a stronger Neoproterozoic age peak, etc., on through the different continents. And I can come back to these if someone would like a closer look at these. So now let's look at them through time. So here's the time-lapse zirconography, and we're starting here at 2.7 to 2.8. We see a strong age peak at about 2.7, and then stepping forward 100 million years on and on, age peaks seem to match the modern sediments until we start getting into these Rhyasian, Siderian sedimentary rocks, where we start to see age peaks that are out of phase with the modern sedimentary age peaks. And so in the modern sediment, we see a trough here at
Я сейчас... Спасибо большое, ага, сейчас я посмотрю.
I'm sorry, I didn't catch that.
I think we'll just hold all questions till the end. So if everyone can just make sure their microphones are muted, and we'll have plenty of time at the end for questions.
All right. So yes, please feel free to type in your questions, and then they'll just be saved in that archive, and then we can go back and address them slide by slide. So again, the modern sedimentary ages show a trough at about 2.2, 2.3 billion, but yet the sedimentary rocks that were deposited between 2.2 and 2.1 billion show peaks within that trough. And then marching forward through geologic time, we see again some other peaks that exist that are out of phase with the with the age peaks of the modern sediments. So if we take all of these dominant age peaks, and I used a signal finder in a MATLAB tool to pick out the ages of these dominant age peaks and plot them all together, we see here these little red dashes. These are the positions of all of the age peaks through time from 2.7 to 0.8 GA. And you can see that there are dominant age peaks in these intervals where you have a trough in the modern sediment. So there was clearly zircon being formed during this time, even though it is represented as a trough in the modern detrital zircon record. If we split this up again into individual continents, now for those of you who are well aware of the regional geology, some of these won't be surprising to you. That we have an out of phase zircon age peak in Africa at about 2.4 to 2.3 billion years ago. Similar here, 2.1 to 2.2. And so in Africa, we see these out of phase age peaks. Asia, similar situation where we see out of phase age peaks. And this was quite an interesting one, that rocks deposited between 0.9 and 1.0 GA show some really strong Mesoproterozoic age peaks that we don't see in the modern sediment. And again, this is just modern sediment from Asia. And so this is not the global. And then in Australia, again, modern sediment from Australia, and then various age peaks that are in phase and others that are out of phase. In Australia, there are no sediments between 2.3 and 2.1. North America, similar out of phase age peaks, primarily in the Paleoproterozoic. And then South America, again, similar patterns as to elsewhere. So if we take the position of all of the age peaks for all of the sedimentary rocks through time, we plot them up as individual ages, and then plot those up as a histogram, as a probability density, we can see that there are very few times in Earth history where there was not a dominant age peak. And so then if I take all of these and rank them based upon their ages, and then calculate the time interval between age peaks. So for example, this age peak here at about 1.4 and this age peak here at about 1.35, that duration is about 80 million years. And so then we plot up the distances, or the time difference between each of the age peaks. We can see that the largest gap, as it were, is about 80 million years. And then the vast majority of the differences are within 20 million years. So from this, I glean that there was never more than an 80 million year period on Earth history, or over this time, from 2.7 to 0.8, where there wasn't some major zircon growth event. Now, let's step forward in time into the Phanerozoic and get even finer resolution. Now, the geologic record of the Precambrian gets a bit sparse, and so I was restricted on how narrow I could take the bin width. So where Steve Parman did 500 million years, in the Precambrian, I did 100 million years. But here in the Phanerozoic, we can get this down even further. And so here we've got every 20 million years. So this is, again, detrital zircon from Asia. In the modern sediment, we see 3 dominant age peaks. And then if we look at this, at the ages in sedimentary rocks, as we step through time from 580 to 560 through, we see the marching forward of this dominant age peak that is out of phase with the modern sediments, and then becomes in phase, and then continues to march forward until it is out of phase again in the late Paleozoic, and then stepping forward from 280 again, it marches forward to in phase, to out of phase, and then once we get into the Cenozoic, we see these three dominant age peaks. See a similar thing from South America. I've got here a map of South America showing where all the samples came from and then colored by their depositional age. Similar situation, we see out of phase age peaks marching through time until they become in phase here at 260 to 280, and then marching forward with time until again they are out of phase and then back into phase and out of phase until the present. So again, this seems to imply that there was never a time in Phanerozoic magmatism in Asia or South America. I did similar experiments with Eastern Australia and Zealandia. That there was never a time where there was not a major episode of zircon growth. So from this, I've got Steve's original conclusion here on the left, and then I've got my new conclusion that the peaks and troughs do not persist in sediments of different ages on various continents, indicating that crustal destruction may control the position of age peaks or troughs. And so I guess where I enjoyed this experiment because it was effectively just an attempt to reproduce what was previously done, but with a larger data set at a higher resolution, at a smaller bin width. And so using the exact same parameters, the exact same methodology, the exact same type of data, we then got very different results. So, this is this paper was recently accepted in the American Journal of Science, and so keep your eyes open for that. And then the last things that I'll talk about is where it starts to get really arm wavy. And for those of you who know me well, you know that I like to wave my arms around wildly in speculating about tectonics and secular change in tectonics. And so I've got here some cumulative proportion, some cumulative probability plots of the zircon ages through time. So these are our 100 million year bins of zircon ages as they span from about 3.8 all the way to the present. And then those are colored by their depositional age, again, from 3.8 to the present. And then following the procedure of Kewet et al. In 2012, I believe, where we take the age of the zircon and we subtract that from the depositional age. And so we basically normalize the depositional age to 0 and then plot all of these cumulative distribution functions on top of one another. I then looked at the changes where we have very, very unimodal populations that have very old depositional ages to where we have more multimodal populations with very young depositional ages. Now, no surprise here, right? As time goes on, there's a larger diversity of the ages of magmatism, and so we would expect more multimodal age distributions in younger sediments. No surprise. But if we take just the standard deviation of each one of these age spectra and then plot them through time, that's shown over here in this gray bar. So this is the standard deviation of all of the age data. Again, this is the zircon age minus the depositional age. And we plot that. We can see that increases through time, again, highlighting the increasing diversity of zircon ages through time. If we just take those zircon that were deposited within 250 million years of the age of the zircon, we see that those do not change through time. So those short residence time zircons, so those zircons that were formed in a magma chamber, and then that magma chamber or volcano brought those zircons to the surface, those zircons were then incorporated into sedimentary rocks within 250 million years. We see that the standard deviation of those age populations doesn't change, implying that the residence time, magmatic residence time, does not change through time. Now, that's a bit of a stretch, and I realize it's a very simplistic analysis of residence times, but that's my first approach. But what's curious about, if you just look at the all of the data, the standard deviations, I would like to propose that there are some steps in the data. Now, we've got just the raw data in gray, but I ran the raw data again in 100 million year bins through a step change analysis. This is a conjugate partition recursion algorithm that picked out two step changes, one at 2.1 billion and one at 0.8 billion years, arguing that the degree of modality, the multimodal nature of these distributions changed dramatically at 2.1 billion and again at 0.8 billion. Now, these numbers probably are of some interest to many of you, and to further highlight this, I've got some multidimensional scaling where we've got the standard deviations of sediments that were deposited between, from 3.5 to 2.1 billion in blue, in green 2.1 to 0.8, and then in red 0.8 to 0.0. There's some overlap here between the 2.1 to 0, but there is an increasing amount of separation through time. So, why do I think these ages are significant? Well, in a recent paper by Mike Brown and Tim Johnson, they showed that metamorphic patterns change pretty dramatically at these times, where as we come from the end of the Archean into the Proterozoic, we see a bimodality of metamorphic gradients developing, where we have high pressure temperature and low pressure temperature, different metamorphic gradients. And then we see again, starting at about 800 or so million years in the Neoproterozoic, we see the beginning of blue schist metamorphism. We see large quantities of blue schist, and again, increasing bimodality of metamorphic gradients through time. This was also shown recently by Holder and others, that using the same types of data, metamorphic gradients, we see that those become increasingly bimodal through time, and that this starts post 2.2 billion years, where metamorphic gradients prior to 2.2 billion years show a kind of simple Gaussian distribution that becomes more and more non-Gaussian, more and more bimodal with time. I would posit to you today that we see similar trends in the detrital zircon ages through time, that the sediments that were deposited between 3.5 and 2.1 billion years show very much unimodal age distributions, and we have a step at about 2.1 billion showing us an increasingly multimodal proportion of ages, and then again at 0.8 another step to the highest degree of zircon diversity, and so we're seeing these coupled changes in the sedimentary record, detrital zircon record, and the metamorphic record. So the next question, and again, this is where things get really thin. Is it 2.1, 2.2, or 2.3? And so I've kind of thrown around all three of these numbers in the talk. So how do we distinguish what was going on during this period of time? And again, it's probably no surprise that I'm going to talk about the tectonomagmatic lull. And this is some new data that I've been working on with Brennan Keller. And so as many may be aware, in 2012, Keller and Schoen showed that there was a dramatic change in igneous geochemistry across the Archean Proterozoic transition. Now, when we evaluate the record of igneous rocks between 2.5 and 2.1 billion, there's not a lot of rocks of that age, and therefore there's not a lot of data to really constrain when that specific change occurred. So with the help of Tong Li and Hugh Amoria and others, we compiled a large database of igneous rock geochemistry across this important time interval and combined it to Brennan's compilation, mostly from EarthChem, and ran the same algorithms. And so this is very, very preliminary results. Brennan and I are still working this up. But we see in mafic rocks, we see a change, not at 2.5 as was previously proposed, but a change between 2.3 and 2.2, which sits nicely straddling the tectonomagmatic lull. And then also new data continues to come out. And I'd like to get Mike's opinion on some of the new data from the Paleoproterozoic low temperature, high pressure metamorphic rocks that seem to first come into existence after this tectonomagmatic lull at about 2.3 to 2.2 billion. And so there's clearly something exciting happening across this important time boundary, but also something happening across the kind of late Neoproterozoic, and I think that where previous attention has been paid significantly to what's happening during the zircon peaks. We want to understand supercontinents, when they were being assembled, the various magmatic and tectonic features of those supercontinents. I think that though there is still a lot for us to learn with the troughs, what was going on during these lulls where we don't see a lot of magmatism and a lot of orogenesis. Despite the fact that we don't see a lot of it in the preserved record, it is clear from an analysis, this time-lapse zirconography, that there was crustal growth, there was zircon growth during these times, and I'm excited to explore those times further. So thank you. That's all from me, and I'm happy to take questions.